this chapter, and then I'm just going to keep on moving into the next chapter because it carries on that there. Well, I've got to pick up the pace a little bit here. This particular section right here, get to the start of it here. Okay. What we're talking about here is decision making, and we're doing some comparisons. Does this? Yep. At least I can use the pen today. So that's the other mystery in life. Does my pen work? And I've discovered in this classroom, some days it does, some days it doesn't. And it doesn't matter whether I'm using HDMI or the VGA adapter. It's the mood of PowerPoint that there. So, but regardless, we can make decisions, and programming would be impossible if we weren't allowed to make decisions as we're going through running our code. And we make decisions all the time in life. You know that there. You go into a store, a lady looks at a pair of shoes, and she looks at the price and may decide if the price is less than 50 ringgits, she'll buy the shoes. If they're not less than 50 ringgits, she won't buy the shoes. Right there. I mean, we do that type of thing all the time in life. Right there. Guys will look at a motorcycle. If it'll go over 150 kilometers an hour, they'll buy it. If it won't, they won't buy it. That there. So a different set of priorities. That there. So we do calculations, and we can make decisions. That there. And this section actually covers the simplest of which is the if statement. And the if statement just simply looks at something in a condition and decides yes or no. If the answer is yes, it will execute the code in the block following the if statement. That there. It's all right. It's okay. That there. Actually, I thought I might start early, but I was actually late, I think, too. So, right there. Later, we're going to see more complex data, decision-making blocks. But the if is the most is the simplest of these types of that there. So we have something called a condition, and the condition evaluates as true or false. That there. So, if a woman has a baby, it's either a male or a female. It can't be somewhere in between, right? Of course, you can argue with the people in San Francisco and London and some of the LGBT groups that there. I think it's LGBT, but that there where there's the lady boys in Thailand and that there. But typically, we'll just assume at birth that a baby is a male or a female, right? So it's true or it's false, right? Now, if you're talking about being married, you're either married or you're not. You're not halfway married. Now, you can be married but separated, but you're still married. That there. You could be going through the process of a divorce, but you're still married until the divorce is final. There. So these are things that evaluate as true or false, right there. So conditions only have two outcomes. When you evaluate them, they're either true or they're false, right there. If a condition is true, in other words, it's met, then the body of code following that is executed. That there. If the amount of money in my bank account is greater than X, Y, Z, I can go on vacation, and a whole lot of things can happen. If the money in my bank account isn't greater than X, Y, Z, some amount, I don't go on vacation, which means I don't catch the train, or I don't buy a train ticket, I don't make hotel reservations, I don't pack my luggage. I do a whole series of things if the condition is met. But if the condition is not met, then no vacation. I go back to work that day. That's it. So that's essentially what happens there. So whether the body's are executed or not, that's there. We complete the code in that there. Now we won't get so much in the relational operators, but in C, a condition can be in the expression that generates either a zero or a non-zero. So if we have a mathematical expression that evaluates as a zero, C treats that as false. If it's a mathematical operation that treats it that the answer is something other than zero, C will treat that as true. Because all it does is, and without getting too complicated, C becomes machine code eventually. Right there. Computers don't run C. We can write C, but we go through the compiling process and the linking process, and the outcome of the linking process and the compiling and the linking process is a file with a .exe extension, and that's binary machine code right there. So in that binary machine code evaluates as either true or false if we put an if statement in there. And when it does the comparison, it looks for a zero. If it's a zero, it's a false. If it's not a zero, then it's a true right there. So I won't get there. So now there are some expressions that you can put into a condition that will cause all kinds of errors. And this discussion right here gets into the one especially when we're doing a condition. This is the list right here that we have here. So some of these are the same as you would have in algebra right there. But the two that definitely cause headaches, and the one that really causes a headache is this one right here, that equal right there. We would write that if, and I don't know that there, if A equal B, then do something right there. Right there. So then there's an example of that right there. If we leave that second equal sign in and write this as if A equal B right there, what that does, and this is where it gets really, really complicated, and one of the reasons I hate C as a first language is that will actually assign A to be equal to B. It does an assignment there, and of course that's going to evaluate as true because it's going to go ahead and do the assignment, and it's always going to evaluate true. And we're going to actually change the value of A. We're not doing a comparison. We're making it equal to B right there. And that just causes all kinds of heartache and grief for young C programmers, especially those that come from other languages that don't have the equal right there. So the not equal, you'll see this little expression, this exclamation mark, that's a not symbol. And we can use that in all kinds of various places right there. But this just simply says that if X is not equal to Y, then we do something. But the X equal Y is the one that's going to cause you headaches when you start writing code. That's there. Because you think if X is equal to Y, right? That's what your mind is thinking. But C expects to see two equal signs if it's up there. Now we can make more complex things such as if sex equals F and age greater than 20, marriage material equals true. We could write, expressions like that. Assuming a guy is 25 years old and is looking for a wife, right? Now, first off, his first priority is the gender equal to F? Is she obviously he's looking for a female, and then he's looking for and he might also say if gender equals F and age is greater than 20 and age is less than 30. So now you're putting more conditions on a potential spouse. He doesn't want her to be too young. Under 20, he's got to raise a daughter, essentially. I'm not picking on any gals under 20, but that there. But he wants, he's looking for a woman that's above the age of 20, but he doesn't want a woman that's above the age of 30. So somewhere in that 10-year range. Out there. And of course, if you go to any of the dating sites, you'll see that people all put all kinds of these ranges in there. I'm looking for the ones I've seen is I'm looking for a Caucasian male between the ages of 45 and 60, and and a whole list of conditions out there. But again, we can put all these conditions in our code right there. But these are the basic operators we've got. Greater than, less than, greater than or equal to, less than or equal to, and not equal to. So those are the 6 that you can use. And we can also, make complex ones, which this chapter doesn't do, but they do in later chapters, where we can put ands and ors right there. So in other words, we can have a condition, and I'll just make one. Oh, what is my computer doing here? We can have a condition. This might be for a lady right there. And we can say if gender equal M right there, and we'll see this age greater than, we'll say 30. I'll put another parentheses, and age less than 50 right there. Put a 5 there. And then I'm going to put another parentheses here, right there, or income greater than, we'll put a bunch of zeros in there, right there. So in other words, this particular lady says, first off, it must be a male right there. And it's got to be between the ages of 30 and 50. So we'll assume that this gal is one except a husband between the ages of 30 and 50. But if he happens to have income greater than 20 million ringgits a year or a month, she'll put up with the 75-year-old guy right there. So, I mean, but you can see how complicated these decision-making processes can be. That's there. And we could do the same thing with a guy. We can just change that to an F. That there. That there. I might look at the 85-year-old woman who's worth 2.5 million ringgits, right? Or who's making that much money. That there. I've always been. I don't know if they use that term in Malaysia. They call them sugar daddies for rich husbands, right there. Some young lady in her 20s will marry a guy in his 70s that's filthy rich that can support her in the way that she wants to be treated. That there. So I've been looking for my sugar mama for 60 years and I haven't found one. I always seem to find wives that expect me to work and pay the bills out there. So, but in this particular case, you can kind of get the idea of how we're using the words and. Now I'm using the words and here and or. Later we'll find out that that's not the correct syntax. It is for some languages. You know, the or is actually is a line, and the and is two and symbols, but right there. But you know, you kind of get the idea of how we can structure these Boolean expressions. That there. And later on, we'll talk about Boolean algebra to a small degree. Now, you've taken a course, or have you taken a course in digital electronics? I think Dr. Lillick teaches it. Out there, I used to teach it, but I think she teaches it now. Out there. But if you look at Boolean algebra, Boolean expressions evaluate as true or false. So here we've got I came up with an expression for looking for a spouse for a young lady that, wants to make sure first off that she's marrying a male out there, which is probably, a good thing, in most places out there. But then had some age requirements. There's probably some other requirements such as weight. I would get kicked out of most algorithms for that. I'm too fat for that there. But I've actually seen people that make the requirements must weigh less than 150 kg or something like that. Which 150 kg is pretty big. I'm not that big that there. So, but you can kind of get the idea that we could come up with these various expressions. So use this example, compare two numbers right here. This is actually some code right here. And what you're seeing here is this is the syntax for each one of these here. Now this particular code, and again, I'm going to talk about the code and then I'll skip the slides that go through and explain the lanes that you've got the slides to read that they're, but it goes through that they're. Now, the one thing that this does a little different than we've done before is if you look at the scanf, notice that there's two placeholders there. Before we always entered one number at a time, right? So now this is asking us to enter two numbers right there. It says enter two integers, I'll tell you the relationships they satisfy right there. So, and then we're doing a scanf and we're putting a %d space %d close quote. That's our format string. Remember the scanf is formatted input from the standard input device, which is the keyboard. That's there. Later on, we'll look at, if we've got time, fscanf, where we read from files. But scanf reads from the standard input, which is the keyboard, and we're asking the person to enter two numbers there. So you don't have to do each number independently. Now you could go back and do this the way you did adding two, where it went through and added two numbers, calculate the sum. In this particular case, we're going to go ahead and just say we enter 35 and 50 or something like that. Our first statement here is it says that if num1, and note the equal num2, not num1 equal that there, we printf %d is equal to %d. Now again, the %d's are placeholders, and we're going to print num1 and num2 there at that location. And then we close the bracket. Note here that we've got an opening and a closing bracket. That's there. In this case, we don't need those. And the reason we don't need those is that we've only got one executable statement in the if statement right there. So The opening closing brackets are needed if there is more than one statement that's there in the block of code. In this case, we've only got one statement, so they're not really needed, but for sake of readability, we place them there. Then we repeat this. If num1 not equal to num2, we do our printf again. If num1 is less than num2, we do our printf. If num1 is greater than num2, then we do our printf. If it's less than or equal to, we do our printf. And if it's greater than or equal to, we do our printf. And notice each one of these, and I'm not going to circle all of them right there, has a opening closing bracket. And then we have at the very end our little bracket here, and that one goes back to here, right there, to the main one. One of the biggest problems that programmers have, and I'm going to say programmers, I'm not just referring to you young people that are just learning the program, I'm talking about people who have been doing this for 20 years, is keeping the opening and the closing brackets separate. The way that you do this is you'll notice that these line up with each other right there. You see right there that I tabbed everything in the if. So all this is in one tab over, and whenever I have an if, it's all tabbed in one more. That's there. So that you can try to keep your braces together. I've been known to print out 5 pages of code and sit there and draw lines between opening and closing braces until I found the ones that didn't match. And you will, one of the most common errors you'll find is you'll get expected ending brace or expected beginning brace or something like that. In other words, it's got a mismatched pair. They have to match. Anytime you have an opening brace, somewhere down here there has to be an ending brace. I can have another set of braces in between. Again, that's a pair. I can have another pair in here. And then I can show this pair goes to here, this pair goes to here, and this pair goes to here. And trust me, I have spent more than probably 100 hours of my life sitting down with pieces of paper taped together, or back in the days of the old dot matrix paper where the paper was on a continuous feed, that they're stretched out and lining these things up with different color highlighters in order to, until I finally got to a point that I had an extra brace buried in here someplace. We'll put it right here. There was an opening brace there that I forgot to include. That there. But it's one of those most frustrating debugging tools that problems you'll have. And you may not have it in this class because we're keeping our programs down under 20, 30 lines, that there we're not getting into pages and pages and pages of code like you would find in a major project. Our biggest project might, our final project might be 3 pages of code. So, and again, I've worked on projects that were, into thousands of lines of code, 20, 30. Well, the breathalyzer, if you count all aspects of it, in the breathalyzer project I worked on, I should point out that one had multiple processors, so we had multiple programs running on multiple computers in the same hardware system, right there. And that one there probably had about 400 pages of code altogether. So I've worked on some things that were fairly long. This is just some examples. Notice that as we enter the two numbers, that you put a space in between them. You don't put a comma in between them, right there. If you want a comma in between there, it's a little awkward, but you can do that as part of the scanf command. You can put the comma in the string where it's expecting a comma right there. And you'll notice here that 3 is not equal to 7. 3 is less than 7. 3 is also less than or equal to 7. So when I enter the numbers 3 and 7, we get 3 positive results right there. I enter 7 and 7, we get 3 positive results right there. So it's possible to meet more than one set of these relational operations. If we have the less than or equal to, that's there, and greater than or equal to, we put two numbers of the same, it's going to meet all three. It's going to be less than or equal to, it's going to be greater than or equal to, and it's also going to be equal to. Right there. If I put 3 and 7, it's going to be less than, it's going to be less than or equal to. And it's going to be not equal to, so it's going to be 3. So as you look at this here, all of these, it just so happened to have equal to match 3 of the relational operators right there. So again, this just covers the same thing I talked about. Placing commas when none are needed between conversion specifiers. In other words, as I mentioned, the %D space %D, you don't put a comma there. And when you run it, you don't put a comma there. That's it. So, and this just kind of goes through and just this is another one that I didn't mention. I'm glad I'm going through the slides. But if I go back and I look at the code right here, notice that there's no semicolons after the if before the opening brace. What happens okay, maybe I closed right there. When I have an if, I have an if right there. Ignore that right there. And I've got some condition. I don't care what the condition is. And you'll see me write this in shorthand where I put an opening and closing parentheses, and I put a dot in between. That just means any condition. Whatever statement follows after this, it's going to do. And then when it sees the semicolon, it stops. Now in this particular case, I didn't put a brace. Because remember I said that if I only have one statement, I don't need a brace. Right there. So I can have if A equal B, printf equal, and I don't want to type much, or write much, so right there. I can do that. That's perfectly legal. That's legit. I have one statement and one statement only. But if I do something like this, if A equal B, I put a semicolon and then I put a brace here, right here, like this here. This semicolon right here, right there, ends that statement right there. So it's going to say if A is equal to B, well, we're not going to do anything anyway. Right there. Because that semicolon ends the statement there. Here, I put the semicolon at the end after the executable statement. That's there. So when we have an if, we have the condition, parentheses, and then an executable statement. Now, if you have more than one executable statement, you put the braces to denote the fact that there's more than one statement. If you only have one executable statement, you don't need the braces right there. But the default in normal C is that it's going to execute one statement before, and that comes before there. A complete if statement right here looks like this right here, where we have if, parentheses, a condition, then an executable statement, and then a semicolon. That's our if statement. Now the way he's teaching, and the most common way, is instead of putting the one executable statement on the same line and putting the semicolon at the end of the line, is that you code this with if A greater than B, we'll change it right there. And then we put the opening brace there instead of the semicolon. Down under the I someplace, we put the closing brace. And inside here, we have all of our executable code that we're going to run if we want, if the condition is true, right there. So that's the way the if statement's the most commonly used. That they're going back to our code here, every one of these if statements only had one executable statement in them. So I could be a lazy person, take out the braces, take out the carriage return, and put if num1 is greater than num2, parentheses, printf, and then whatever, I'm looking at this one right here, right there. I can take this brace out, take this brace out, I can take this out, and I can take this and bring it up to the end of this line right there. And do this as a single line instead of 3 lines. Now, this is the normal way that people do it. What I'm showing right here is because this is the most readable and clearest way to avoid mistakes. But some of you may find yourself in a position of inheriting somebody's 300-page stack of cryptic code in which they do some of those things out there. And believe me, there's nothing more challenging than trying to fix somebody else's code. That is that there. So, okay. That there, let's just kind of go through that there. I think that pretty much ends this chapter right there. There's some other things here where they talk about, so, left to right. I'm at there. I usually just use parentheses in order to make sure that my statements are clear. Right there. This is a added list of keywords that you cannot use for variable names or function names. Auto, we won't get into do, go to, sign, unsigned. We haven't covered what these are all for. They'll be covered in later chapters, or most of them. But this is just a list of words you can't use right there. And also notice that things that are been added in the C99 standard, that was in 1999. They added underscore bool as the type, complex, imaginary. In the standard for 2011, they added these others, and to be honest with you, I've never used any of these other ones right there. All right, let me jump out of here, and let me bring up chapter 3. Hopefully, I'm thinking. and browse chapter 3. I'm going to just jump in here. I'm going to start this because, again, as I said, I'm not feeling 100% here, but I might as well start the chapter, and then tomorrow we'll continue on. This chapter here actually is the one that starts teaching the idea of developing structures for our program. Right here. This is where we get in. This is right there. This chapter covers the basic problem-solving techniques. Right there. And how to develop an algorithm from top-bottom, stepwise refinement. In other words, how do we start thinking like a programmer? And I'm going to change that term of how do we start thinking like an engineer as well. How do we start thinking like a problem solver? Everyone in this room is supposed to be getting a degree in electrical engineering, right? A bachelor, B.Eng with honors in electrical engineering, right there. So now in the States, we don't have different degrees for electrical engineers, electronic engineers, and computer engineers. They've started to, but that used to be all electrical engineers were under that category, electrical electronics. But all engineers have to solve problems. The system that I worked under in the U.S., I was, and I still am. I still keep my registration complete. I'm a professional engineer, which a professional engineer is similar to what they call the IR here. Actually, a professional engineer is a much more difficult task to get. Most engineers don't get it because to become a professional engineer, you have to prove competency in all phases of engineering. In other words, I had to answer questions.
Sorry, sir. Sorry to interrupt.
Yes.
I wanted to meet my roommate.
Oh, okay.
Sorry, sir, for interruption.
Okay. Well, that only cost you 20 ringgits, so be sure you give it to him to pass on.
Thank you, sir.
That's there. I charge fees for everything. That's there. That's there. So, otherwise, I can't. I'm looking at retirement soon.
Thank you, sir.
You're welcome. There. But as engineers, you have to solve problems. And the key thing that when I talk about solving problems is that quite often the problems that you have to solve are not in the area in which you're supposedly an expert on. I can think of one project that I worked on, and one of the advantages of being old, not being able to walk very fast is not one of the advantages. One of the advantages is that I have lots of stories to tell. That's there. And these are not made up stories. These are real projects I've worked on. But I worked on a project one time where we were testing sonobuoys, which are things that are dropped in the ocean to look for submarines, for leaks. And the way that we look for leaks is we pulled a vacuum on the sonobuoy, and then we pulled a vacuum on a reference tube right there. And the original design was getting all kinds of failures. And what we did, and I spent 3 months on the project full time. I was brought in as a consultant to figure out why this test kept failing. Because from a theoretical standpoint, it should work beautifully. And as it turns out, the failure was caused by a difference in thermal mass between the unit under test and the reference unit, which we knew did not leak. As we pulled the vacuum, it dropped the temperature in both units. However, the unit which had no thermal mass in it dropped much farther down and went back up much quicker. Well, Boyle's gas law says that the volume of a gas is equal to It's temperature times the mass divided by the pressure which is on, or something like that. I can't remember Boyle's gas law at the time. But the whole problem in solving an electrical problem, again, this was a computer designed piece of test equipment. So we were doing all this in software. And I'm sitting there going through the software. Software looks good, nothing can't figure out. The hardware looks good. And it comes to find out that if we opened up our reference tank, our reference buoy, and then we threw a handful of garbage in it, which happened to be the inside of a normal buoy. We took an defective buoy, took all the stuff out, and just threw it in there, just to give it the same thermal mass. Everything worked perfectly. But this is a problem that had nothing to do with electronics, had nothing to do with programming, had nothing to do with what I was, that was my specialty right there. I was talking to a gentleman a while back. This is not a true story from my perspective, but it was from his perspective. He works at Intel up in Penang. There, they have a big foundry. And they're having all kinds of problems with the ICs sticking to the vacuum robot arm that picks up the IC and puts it in the carrier. They're sticking. And of course, that causes all kinds of problems in automatic test equipment. The problem in that particular case was they had 2 bottles of cleaning solution to clean out the vacuum lines that were the same color in similar bottles, and people were using the wrong cleaning solution to clean the vacuum lines. That's there. Solution, store the cleaning solutions in different places, mark the bottles better, train the people. But again, both these problems had nothing to do with the engineering in particular right there. So when we look at problem-solving techniques, that's what engineers do, is they solve problems. Most of you will probably go to work in either the construction industry, the power distribution industry, or the manufacturing world right there. So you're going to be quite often summoned into a particular neighborhood or village or shopping complex that the lights keep going out or there's problems that there. And then you're going to discover that the problem actually has nothing to do with electricity. It might have to do with the placement of the breakers too close to a staircase and people bump into it as they walk down the stairs. And I'm just throwing that as an example. I don't know if that's the case, but you'll start seeing that problems are not necessarily part of what you're trained as, part of your training. You take courses in differential equations, you take courses in matrix algebra, you take courses in that, and you'll find that 90% of your time when you're out working as an engineer is you're solving problems that don't have any mathematics involved, they don't have any engineering involved, but they're just problems that are related to that thing. So that's what engineers do more than anything else, is we solve problems. That there. So the better you're at you becoming at problem solving, the better engineer you'll be. Now the difference is there are some, if you're working for NASA, like the U.S. or Boeing, and you're designing new aircraft or new spaceship as a design engineer, of course, then you're using those types of skills. But pretty much, I'd say 90% of the people in this room are probably not going to be working as design engineers. That's there. I did for a long time, but most of the engineers I worked for were in the manufacturing or the test equipment design. That's there. Most of the people that work for the power company were most engineers in both the U.S., Europe, and especially Asia are not doing design work. They're doing troubleshooting, maintenance, repair, keeping things going, Installing new equipment kind of falls under that category a little bit. But so a lot of the skills that you're picking up in the university, you don't really use on a day-to-day basis. I can't remember since I quit working for the Sonobuoy group, when we were doing some, signal processing, trying to tell a dolphin from a whale from a submarine, where I had to do any differential equations or math operations. That's there. I don't, even when I worked on projects where we're doing some of the targeting stuff, it was almost all done in algebra. Calculus, rarely used in real engineering work. That's it. So don't tell us one I said that. Okay, so we're going to be looking at basics problem-solving techniques. That's there. And unfortunately, in a 15-minute discussion, I can't teach you everything about how to solve problems right there. That's a thought process that you need to develop working on homework assignments. I'll probably give you some projects that force you to do some of that, but showing that there. Developing algorithms of the top-down stepwise refinement. In other words, how do we solve our problem in a top-down stepwise? Top-down means that we start out there. I want to change the engine of the car. I start out with 3 basic parts. 1 is I remove the engine. 2, I find the replacement engine. 3, I put the engine in the car. And then 4, I test it, right? Now, obviously, there's lots of steps in each of those 4 steps. Out there. If I'm trying to bake a cake, I mix all the dry ingredients together. I mix all the wet ingredients together. I combine the 2. I turn on my oven or my steamer. I know that a lot of cakes are steamed here instead of baked. I set up the temperature. I place it in the oven, and I keep checking until done, right? But there's a lot of steps in there. Mixing the dry ingredients means that I'm going to find flour, I'm going to find sugar, I'm going to find this. I have a list of dry ingredients that have to be mixed. I have a list of wet ingredients. It might be milk, it might be eggs, it might be water. I don't know. It might be that there. So we will be using the if selection. We'll be introducing something new called the if else right there. The if else means that I have a condition. If X is greater than B, then do this. Otherwise, do something else. Right there. So if gender equals male, buy truck for birthday. Else, buy sewing machine. That there. Just kind of an example. But you look at a condition and you have 2 options right there. So right there. We'll be looking at counters where we do things a certain way, or a sentinel. A sentinel is a truing value. Do something until all the data has been processed. Right there. And then, of course, word structure programming, which is a huge topic there. Then the last one's easy, the decrement, secrement. So these are all the various things right there. So, and I'm probably just going to talk about, I don't know what my time is. I have 49 minutes. I can go a little bit longer right here. Okay. Before we write a program to solve any particular problem, you have to understand the problem out there. Now, we used to have a saying a lot of times in a number of industries that I've worked, and what are the most difficult things sometimes is finding out what the problem is. Now, we used to sometimes, if you're dealing with areas such as mental health, I know that's not a major area that most of you that there, but when I was a young person going to college, I had the experience of working part-time. I went to college a little later in life, and I was married with 2 kids, so I had to feed the 2 kids. They get hungry. I don't know what it is about children. They expect you to feed them, right? You know, the grocery stores expect you to have money to buy that. So, but I worked at all places, a state hospital, mental hospital. So I have a pretty good experience dealing with people that are not quite stable out there. You know, I always consider it good training to be not a faculty member, but to be an administrator in a university system. Because a lot of faculty aren't stable either. You know, they're a little crazy at times out there. But you know, one of the things we used to say at the hospital is the biggest problem is getting the person with the problem to realize they have a problem. Now, when you're dealing with engineering problems, you have to understand what your problem is. What are you trying to do? That's there. And again, the problem that you're trying to solve is, I'm trying to write a program to calculate the payroll of every employee at UniKL. Right there. So you have to completely understand what are all the parameters involved in calculating the payroll. You know, I have to look at the base salary, whether the employees on a contract basis, whether they're getting paid housing allowance, whether they're paid a transportation allowance, whether or not they get insurance, whether or not they have to do EPF withdrawals, whether or not they're taking out Zakat, is that the correct pronunciation, what their income tax rates are. All these calculations, all these parameters have to be part of how you solve the problem. Right there. So you have to thoroughly understand the problem. If I want to build a building, I have to understand what type of soil is underneath this building, what type of bedrock is down underneath the soil, what is the water table, how much water pressure is placed on this during heavy rains. One of the problems that Malaysia has is, it's not just Malaysia, it happens a lot in California too, but so I'm not picking on Malaysia, is you get heavy rains in areas where people build houses and condominium complexes on the side of hills. And people love to live on the side of a hill because you got a great view of the valley down below and the city down below, and if you're near the ocean. The houses up on the side of a built in the side of a hill, they bring a lot of money. I've got a son that lives in San Diego, about 4 blocks from the ocean. Unfortunately, he's not up on a hill, and even more unfortunate, between him and the ocean happens to sit a great big Navy base, so he's got a great view of the Navy base and not of the ocean out there. So actually, he's about a couple blocks from the Navy base, but he's not, you know. So his house isn't worth that much. But if he had a house up on the hill a little further away that could see the ocean on the other side of the Navy base, those houses would be worth a lot. Well, when things rain, soil washes away if it's not properly anchored to the ground. Well, if you have droughts, soil dries up, right? All the vegetation that would normally hold the dirt together to keep the soil from washing away and keep your building from sliding down the hill gets washed away. And the next thing you know is you've got a building that is sliding down the hill. You know, but I used to live in an area in KL called near Bansar Pantai Hill Park, a condominium complex. Some of you might have heard that. They had problems in the complex I used to live, where one of the condo units actually slid down the hill into the neighboring condo unit. Right there. Again, the problem was the soil dried up because of not enough rain, and it wasn't anchored into the bedrock. And that's a civil engineering problem. but it's part of the problems that, as an engineer, you should be looking at across the board on any project you look at, right there. You know, and I'm going to get off the subject a little bit and talk about the fact that as an engineer, one of the things engineers are supposed to do is you're supposed to look out for the safety and the well-being of your fellow citizens on any project you're working with any company you're working with. And it gets to be very, very awkward and difficult at times because sometimes the owner of the company that they're, and I'm not picking on any company, any nationality. This happens everywhere in the world. But the major goal of the CEO of any company is to do what? Make money, right? Yeah. I mean, Intel, which is a great company, they've been around for the last 40 years. They invented the microprocessor. They've been around probably closer to 50 years. They started in the 1960s out there. Intel was not formed to make microprocessors. They were formed to make the four founders, Gordon Moore being one of them, and Noyce being the other, and I can't remember the other two names, but the four founders, in order to make them a lot of money. That was the goal of the company. That there. So sometimes the CEO of the company and the top management are often more concerned with profit than they are safety and reliability of their products right there. Samsung got a big black eye roughly about 2 years ago when they started releasing phones that exploded in people's pockets, right? Everyone remember the Note 7, the exploding phone that was banned from that there. Some engineer took some shortcuts out there. I read once, I don't know how true it is, the problem is the battery was the exact same size as the battery compartment. So when you charged the phone or it was draining rapidly for whatever reason, things expand when you draw a lot of current from batteries. So the battery would start to expand. When it started to expand, it had no room to expand, so it would just literally blow up. Or, blow that there. I heard that as one of the possible. Obviously, they've solved the problem, and I have a Note 8, which I happen to find a very reliable phone. But again, this is a case where here is a company that somehow took a shortcut, and the shortcuts cost not just a lot of money, but also some hospital bills. I don't think there was any deaths because of the Note 7 fiasco. But there have been people. There's a company that makes airbags. It starts with a T. It's a Japanese company. And there's been literally hundreds of deaths because the airbags have malfunctioned because of a design flaw. That's there. So when we do a lot of these things here, we have to look at these problems, and you have to carefully plan your solution and take into consideration things that are not necessarily part of the initial problem that's there. You have to look for the unexpected right there. So there's 2 chapters this assigned to it, and we're going to kind of go through. An algorithm is a fancy term to mean recipe or a set of instructions. The solution to any computing problem involves a series of actions in a specific order. You're going to bake a cake. You mix the dry ingredients, you mix the wet ingredients, you combine the two, you put the cake in the cake pan, and you put it in the oven, right? You do that. You don't put the dry and the wet ingredients in the oven without mixing the two of them together. That's in the wrong order. You won't get a very good cake right there. So you have to do things in the right order. You're rebuilding an engine of a car. you got to put the head gasket on before you attach the head. Otherwise, you get oil all over the block of the engine, right? You can't try attaching the head gasket after the head has been bolted to the block and the engine is inside the car. You got to completely dismantle the head and everything else, and it's a lot of work. You have to do things in the right order right there. So that's the procedure. That's our algorithm right there. So that they're correctly specifying the order in which the actions are to be executed is important. The order is important. Taking a course in feedback control systems, which involves a good amount of Laplace transform solutions of differential equations. It's probably good if you take the math course before you take your course in feedback control. Trying to take a course without the prerequisite will quite often create a lot of heartache. And believe me, I did that. And I did a lot of sleepless nights as a student when I took advanced linear algebra without taking elementary linear algebra. I got a B in the course, but I also didn't sleep 2 or 3 nights a week. So the order is important right there. So the rinse and shine right there, and this is an example here. Get out of bed, take off your pajamas, take a shower, get dressed, eat breakfast, and carpool to work. That's the order, right? When I got up this morning, first thing I did was I took off my pajamas, then I took a shower, then I got dressed, and then I ate something that I shouldn't have ate with a white shirt, so I had to take the shirt off and wash out my blueberry jam from my shirt and then put it back on. But that was a side note from the algorithm out there. Eat breakfast and then get in my car and go to work. I don't carpool to work. So that works fairly well. But what happens if we get out of bed? You gotta look at this here. We take off our pajamas. That makes sense. We get dressed. Now we take our shower. What's wrong with that? I'm taking a shower with my clothes on. I've already gotten dressed. So the order is messed up. So I show up to work soaking wet. Now back before my stroke, I used to ride my Vespa to work most days, and inshallah someday I'll get to where I can ride it to, regularly back and forth to work. Out there, my doctor keeps telling me to stay off of it, but I ignore him out there. But regardless, I have showed to work soaking wet if it started raining halfway to work. So that there. But regardless, but in this particular case, the order is what's important as we're doing things. So whenever you're looking at a problem, and here we're looking at a simple problem, is we've got an individual that wakes up in the morning and has got to go to work, right? And he has to do a few things before he leaves the house to go to work. Now, if he, for example, goes back to my algorithm here, and if we skip a step, so for example, we skip get dressed, we just happily forget to do that, he will probably find himself at my former place of employment that I mentioned, the state hospital, when he shows up at his desk without clothes, right? Or if he forgets even the 3 of these, which, believe it or not, a lot of American college students were notorious for skipping those 3. I don't know how many young ladies I used to have show up to class wearing their pajamas. They would literally crawl out of bed, grab a donut or something to eat, and show up to class with their cup of coffee and their donut in their pajamas still. That there. It hasn't happened to me in Malaysia, but I've seen more than one young lady show up to class wearing, and usually they're reasonably, I mean, they're not sexy nightgowns or something, but I have seen them show up in pajamas that there. So there are cases where this happens. We have a shopping center in the U.S. called Walmart, which caters to the lower income part of the population. And sometimes you'll see people doing their grocery shopping at 2, 3 in the morning in their pajamas out there. So seeing people out in public in pajamas does occur. But it happens here. I mean, I used to live over at Dr. Carmont. I don't know if any of you know Compound Dr. Carmont. It's, an older part of town. And I used to go out to eat at the food stalls, and I'd see people show up in pajamas out there. But if you're an executive, you probably don't want to do that there. So, okay, I'm going to kind of stop at this slide here. And I've actually done my hour roughly anyway. But we will start with this idea of pseudocode. And pseudocode is an artificial informal language that it's something, you write the code in something that is not really a computer language, but it's not really normal talking. Now, this is an important step because many of you might find it easier to write your pseudocode in Malay than English, because that's the language you think in, right? That there, unless there's somebody whose English skills are much greater than I'm used to seeing, your thought process is still in Malay. Even if I became very proficient and I spoke Malay 75% of the time, and that there, which hasn't happened in years, but my thought process will always be in English, probably till the day I die. My wife lived in the U.S. for 7 years, maybe 7 or 8 years, and watched American TV and spoke to Americans. Her thought process always remained in Malay. So whenever someone said something to her, she had to translate it in her mind back to Malay in order to that there. And sometimes it gets a little bit automatic, and after long enough, people change their thought process. I have an ex-wife who's Malaysian, and she's now lived in the U.S. for 20 plus years. And her son has lived in the U.S. for probably 15, 20 years. And they don't speak Malay anymore. They're not around Malaysians. They now their thought process is in English. So she struggles to talk to her family here in Malaysia because her thought process is switched over into different languages. Pseudocode is normally done in the language that you're most commonly that you're thinking. So you think how you want to write the program. Now, I don't require that you turn in pseudocode as part of your homework. I don't even write pseudocode half the time because I can think in C-like statements. I wrote enough C that I can think like C-like statements. I mean, make syntax errors, but the whole idea of pseudocode is that you simply think out the program. You come out and you look at how the program is supposed to work. You outline the steps of changing the engine in your car. You write out the steps of how to bake a cake. A good example of pseudocode is to look at any cookbook or any repair manual. Because these are algorithms in pseudocode. They're in Malay or English, depending on which language you look at. And they outline the steps it takes to bake a cake, to make nasi lemak. Now, again, some of the ladies, your mother showed you how to do it without recipes and that there. But I'm saying, when I moved back to the States and I wanted to eat Malaysian style food, I didn't have a Malaysian restaurant. I was living by myself. That I bought a bunch of Malay cookbooks, and I had to follow the recipes. And unfortunately, because I'm not a Malaysian and I don't know how to cook Malaysian food properly, even following the steps of the cookbook, it didn't taste the same as the food stalls that I eat at here or what my wife cooks, because the cookbooks say put in a quarter teaspoon of salt. Well, in reality, if you go to the food stall, they reach out and they grab whatever amount of salt they know tastes right for this particular recipe. So they're not, but a pseudocode is the whole idea is you're trying to write the steps to solve the problem. The problem in this case is I've got a bunch of ingredients. I want nasi lemak. So how do I get nasi lemak out of a pantry full of ingredients? First I have to wash the rice, and then I have to add the coconut milk, and then I have to take the pandan leaf and tie it and put it in there. And the first time I saw that, I threw the pandan leaf. I couldn't figure out what the pandan leaf was for, but later I figured it out. And then you have to put it in the microwave for so long, and then that's it. But you have a series of steps you have to go through to make this, and that's the pseudocode. So now a carefully designed pseudocode program should be converted easily into corresponding C. Now that's more easily done from English to C than from Malay pseudocode to C. But it's still, if you write your pseudocode properly in Malay, or your instructions are clear, writing the corresponding C statement should be a straightforward process right there. So with that, as I said, I'm going to kind of quit here and we'll pick up where we left off that there.